Well, this is a real pleasure to come to, where am I here? Harvard University. As some of you know, I have been on leave in the past year, and I thought I would just skip over all that, and then I realized, actually, I better explain. I've been on leave for a year at the Gordon and Betty Moore Foundation, which is a philanthropy in Palo Alto, California. Gordon Moore was one of the founders of Intel, and he took his vast, well, not his last penny, but he put a lot of it in a foundation which has a $6 billion endowment and spins off about $100 million a year for science, for basic science funding. So I'm in charge of that. And you can still talk to me. It'll be all right. And we can still make grants to Harvard University, the Smithsonian, other places. And in fact, we do. Shep Doleman, for example, with the Event Horizon Telescope is one of our grantees. Okay, enough of that. What I want to talk about a little bit is just to repeat some of the obvious things that you need to know. Because when I looked over the program, I saw that there are people who do fast radio bursts and gravitational waves and things. I thought maybe I should just say a few of the things that people ought to know about Type 1a. Then I'll show you that the mystery that we're confronting now is mostly the one of the progenitors and the origins for the exploding white dwarfs. We still don't have that thoroughly pinned down, but we have some additional evidence that shows that at least in one case, it looks like the evidence for a companion in a binary has been seen. That's good. And then I'll talk about the application of the 1As to cosmology, because part of the fun here is that the 1As are a much more uniform set of objects, even though we have a lot of subtle differences in them, and they can be used well as standard candles. So that's it. Let me just say one word about the Gordon and Betty Moore Foundation. Everything in California is backwards. If you have any money left over at the end of the year, they call that a deficit. It's really hard for me. No, we have no deficit. The conservation people have a deficit. Anyway, so I'm talking about Type 1a supernovae. You all know that these are events which have a time scale of about a month. They get bright, they get dim. We think that the energy source for the Type 1a comes from the nuclear burning that takes place in a carbon-oxygen white dwarf, or possibly some variant of that, producing, roughly speaking, a tenth of a solar mass of iron. But the observational part is interesting. Here's Fritz Zwicky, who was the Sri Kulkarni of his time, with an advanced instrument for wide field imaging at Palomar. This is the first telescope at Palomar, the Schmidt, 18-inch Schmidt telescope at Palomar. And Fritz Zwicky undertook a deliberate program to find and study supernovae during the 1930s. And during the 1930s, every supernova they found was the kind we now call Type 1a. So they didn't call it Type 1 at that time. They just called it supernova. It wasn't until 1940 when Minkowski found the other kind, the kind that has hydrogen lines, that people began to talk about Type 1 and Type 2. So while I know it's very popular to say unkind things about our classification scheme, nevertheless, that's the beginning of the trouble. Here is a somewhat earlier image of a discovery of a supernova. This is, of course, taken with an iPhone. This is Tycho out in front of some romantic-looking Uraniborg, and up there in the constellation Cassiopeia in November of 1572 is an object which today we would call a Type 1a supernova. So we know some things about them. For example, we know from Tycho's work that they lie beyond the orbit of the moon. And we know other things from more sophisticated investigations recently. For example, the X-ray observations of Tycho's supernova show you this wonderful interior, which is the hot gas from the shredded star, more or less spherical, and including quite a lot of iron. So when, if the reporter calls and asks you, yes, but what good are they? You can always tell them that if it weren't for Type 1a supernovae, there would not have been 3,200-pound cars built in Pontiac, Michigan. This car was, you could say, built in Michigan, but really the parts for it, that is the atoms, the nuclei, were manufactured 5 billion years ago. So you may think this is an old car, and it is. Okay. So what are they? Here at Harvard, I've been on the faculty for 31 years, and I've had a lot of students in classes bigger than this one. And the exam question in my course that is about what's a type 1a supernova would be graded correct if you said it's an exploding white dwarf, if you said the energy source was nuclear burning from carbon and oxygen up to nuclear statistical equilibrium, not quite, iron. And that leads to a radioactive power for the light source, because we know that the diffusion at the beginning and then the long exponential tail is naturally explained by that, and we'll see, I'm sure, some real models of that. You'll get extra credit for explaining why it's nickel 56 and not iron 56. Because it's even. No, no one ever gets that. Okay, yeah, carbon and oxygen, they both have the same number of neutrons and protons. Okay, but what's the evidence? Well, no hydrogen in the spectra does suggest that we're at the end of stellar evolution of the ordinary kind. We heard a lot of interesting stories yesterday about ways that stars can get rid of their hydrogen. For a white dwarf, it could just be that that's all that's left after burning. There's another clue that's important, although not decisive, which is that they are the only supernovae found in elliptical galaxies. And that suggests that at least in some cases, they're not closely linked to star formation. And in at least some cases, there's a long fuse for the bomb. And of course, we'll see a lot of beautiful work that's been done, showing that there's a good match between spectra at maximum, or spectra, especially at late times, which match up with plausible white dwarf models. The problem is that the inverse problem is hard. There are many such models that match up with the data, and it has not been easy to find an observational clue that will tell you which of the possible paths to making a type 1a supernova is the right one. And we'll hear much more about that today, this morning, and in the panel discussion. Okay. So I'm going to talk mostly about observations, but the real problem is theoretical, that is, understanding the origin. Eddington said, it's a good rule not to put overmuch confidence in the observational results that are put forward until they are confirmed by theory. And so we're in this situation where we have a very good empirical tool, which we've used to map out the history of cosmic expansion, discover cosmic acceleration, infer dark energy. But we still have this kind of embarrassing problem at the foundation. Not that kind of foundation. Okay. So let me just sketch this just very briefly. So here's a light curve just for your possible amusement, because there was some discussion yesterday of the 60-inch telescope at Palomar. I thought I would show some data taken with the 60-inch telescope at Palomar before it was scheduled. The turned out supernova 1972e was found in May of 1972, and I went every night to the telescope and measured those points at the beginning, because the telescope wasn't scheduled until June. Well, that was good. And then Bev Oak used the 200-inch to measure the long exponential decay here. And for a long time, this was one of the longest light curves. Of course, 2011 FE is now a better case. But anyway, so we've known for a long time that there's circumstantial evidence for this radioactive power, diffusive at the beginning, and then where the emission is more or less at the rate of the radioactive energy input at late times, while you come down to the area where the spectrum becomes what we call nebular. And so here's the nebular spectrum. Again, this is from the multi-channel back in 1973, I guess, when we made the observations at 4. And we thought we would be really high-minded and plot things as a function of frequency. So the scale on the bottom, which I cut off, is log of the frequency. But there's wavelength up there for those of you who need the help. And it turns out it looks backwards, of course. And the thing I want to show here is that at very late times, the strongest lines were known even then to be those bumps there in the middle around 5,000 angstroms. And I sat down with my HP 35 calculator, and I made this synthetic spectrum, which is all the emission lines of iron 2. at a temperature that seemed plausible. Ah. Last refuge of scoundrels. Oh, no. All right. So here's this part of the spectrum, and then here's the synthetic spectrum. And of course, what's missing is one of those bumps, which is iron 3. Bev Oak said, you should do iron 3. I said, I don't know where the data is. So anyway, I should have gotten that better. Okay, but this picture, this elusive picture that we have a radioactive source and so on, and that we can match the light curve with input from the nickel, cobalt, iron decay, is something which really ought to be tested directly. And it is only now that that's been possible. So here I show you the data looks kind of terrible. Where's Neil? Neil, this is normal for gamma ray spectroscopy. Would you say?
Low significance.
Yes, terrible is good. But this terrible spectrum, which was obtained over essentially an E-folding of the supernova light curve, shows something, well, underneath you see plotted some lines. But these are the 847 kilovolt line and the 1200 kilovolt line attributed to, I should say this right, cobalt, yes, to cobalt, which you expect to be the energy source for a supernova in this era. So I would say, even though, this has been really hard, someday there will be a better spectrum and it will show the same thing. That is, we finally, I think, have what you could count as real evidence that this story, physical story that we've been telling is correct. But the astronomical story remains quite uncertain. We have a story in which there's a more or less ordinary star, in which there's and then accretion onto a white dwarf. As the white dwarf approaches the Chandrasekhar limit, but doesn't collapse when it reaches the Chandrasekhar limit. That would be marked wrong. As it approaches the limit, the central temperature and density are high enough to ignite carbon, and we think that can happen. However, the evidence for that has been quite scanty. Another story which has been worked out in some detail, and I'm sure we'll hear about this this morning also, is a story in which there are two white dwarfs, and there's something that goes away from the orbit and it loses energy. You should work on detecting that too. Anyway, there's something that goes out of the orbit, gravitational waves, and these things can merge on a Hubble time. And what's been shown over the last several years, Wolfgang Hillebrandt's group has done a beautiful job of this, is showing us that it's possible that that could be the origin of type 1a supernovae. There are even more exotic stories, of course. The two white dwarfs may not collide because of gravitational radiation. There could be a third party, and it's possible for the angular momentum to go out of the system so that the two things there in the middle, the white dwarfs, colored red, the white dwarfs get onto an orbit in which they, with no angular momentum basically, and they collide, having lost angular momentum through the exchange with that third party. This is illustrated here, where you have things that are shot at each other. Oh, golly, you'd think I'd be able to hold on to this button long enough. Here we have things that are shot at each other, and the idea is that they collide right here, and the third party over there is the responsible one. Okay. Oh, stop it. Okay, so what's the story? Why can't we turn to the evidence and find out? All the evidence, almost all the evidence except the evidence I'm going to talk about today, has been pointing toward no leftover companion. So if you look at nearby supernova remnants, here I show you a supernova remnant in the Large Magellanic Cloud, where space telescope observations allow you to look to very faint limits for something to be inside. And when you look in the right place, you don't find it. So there's no evidence yet for speeding companions, no persuasive evidence anyway. The very, very rapid response for supernova 2011 FE permitted very stringent limits to be put on the presence of a companion at the site of the explosion. On the other hand, they are not so stringent that you can't believe there was, there could have been a 2 solar mass star in the neighborhood. In any case, all the evidence so far had no sign of a companion. But not having a sign of a companion is not the same as showing there is no companion, or the companion was a white dwarf. So we have to be careful. I think there is such a thing as fashion, even in science, and sometimes there's a kind of a pendulum of opinion that swings back and forth. I think we should resist the temptation to get on the bandwagon and look for evidence. And of course, the kind of evidence that we would expect to have is the evidence that was worked out by Dan Kazin, and before that in other computations. But here is the idea. Here, suppose this is an explosion, and here's a neighbor. And as the explosion, exploding white dwarf, engulfs its neighbor, it will heat it up. There could be emission from this dense hot stuff here, and you might see it. So there could be a clue in the early light emission from a type 1a supernova from this neighbor as it's being heated. And that paper was written by Dan in 2010, and that made some fairly good predictions. And we've been looking for that, and I want to show you that we do see it a little bit. In the case of supernova 2012 GC, we were able to make observations pretty early. So there are a bunch of places here. This is our observatory. This is, of course, Alex. This is LCO. Swift played an important role. ROTC's still doing important stuff. And we were able to put together a light curve in various colors and to compare that with the models that Dan Kazin had computed. So let me show you what the models look like and what the data look like. So here you see computations in the ultraviolet, the blue, and in the V band, the visual band. And the idea is if you have, let's say, a red giant as a companion, you get a lot of emission, especially in the U band, from the neighbor when it gets hit by the explosion. So that's a computation for a particular model. And then there are other models here. There's one for a 6 solar mass main sequence star as the companion, and that's the blue line. And there's the 2 solar mass main sequence star as a companion, that's the green line. Now the data is not 100% agreeing with itself everywhere, Alex, but I think that the evidence is, it's interesting, and it could be that what we're seeing is the match between the observations for this object and the model that Dan Kazin put together earlier. I think it's easier to see it in this picture, which shows the color. So this is the B minus V color. Blue is down this way, red is up that way. This black line is what you might guess for a model in which there's no interaction. You're just looking at the color of the white dwarf early on, of the explosion, basically, as it heats up. And if you look at the data for 2011 FE, it goes more or less along that line. Other cases where we have very early observations are these for 2009 IG from Kate and from Swift. And you can see that in those cases, the evidence seems to agree pretty well with the no companion picture. But all this messy stuff down here are the various observations that we were able to do for 2012 CG. And I think in this picture, while it's not a great match, and it certainly isn't something where you would know whether that you would think you had measured the mass or the radius of the companion star, it certainly looks like the light at very early times, this is 17 days before maximum, is bluer than it would be in the case where there was no companion. So that's more or less the story. There could be some other reason for having blue stuff. For example, yesterday when people talked about blue stuff early, they said, oh, it's circumstellar matter. Here we say, oh, well, no, it's not circumstellar matter, it's a companion, a rather dense form of circumstellar matter, I guess. Okay, so that's what I want to tell you about that's what I want to contribute to the story on the origins. Now let me say a few words about what we're doing with the type 1a supernovae. And one important fact is that when you have a supernova, you're seeing it through dust in our galaxy and in a neighboring galaxy. So it's better if you observe in the infrared because you can see through the dirt. Just to illustrate this, I know there might be radio astronomers in the room. It'd be good to illustrate this. So here's a picture of a cloud of dirt seen in the blue B band. And if you look out at 2 microns in the infrared, the dust is more or less transparent. It turns out that would be a good reason for observing in the infrared, but the supernovae provide an even better one, which is shown here. This is in a paper where Casey Mandel took a sample that we'd put together from the CFA and from Carnegie of type 1a supernovae. This shows how bright they are, and this shows how fast they decline. This is the kind of relation that Mark Phillips found and that we know helps us make these tools into better standard candles. There's a variation here of about 50% in the flux, but when you take the light curve shape and colors, you can put it back onto a relation, this blue line, about which there's very little scatter. So that's in the optical. But look over here on the other side. This is if you make the measurements in the infrared. First of all, the corrections are smaller because the going from red to black is the dust correction. And secondly, the relation is very nearly horizontal. That is to say, they are standard candles measured in these bands in the near infrared. So that is nature's way of telling you how to proceed. And the large samples of data that people have for measuring cosmology are mostly not with measurements in the near infrared. So we've taken the step to try to get that advantage by observing in the cosmological distances to get the rest frame infrared. And so let me just tell you in a couple of minutes what that was. We've been using Pan-STARRS, which had a wonderful camera on it that covered 7 square degrees, and the medium deep survey, which many people in this room contributed to, searched for, made observations every 4 days going through a set of filters, and was very good for supernovae at about a redshift of 4/10. So this shows how to find them. Pay attention, Armin. Here's if you have an image and you have a reference image, you subtract it. It has those little tick marks. Everything is good. We were on the ball for this. We got spectra of 358 of the supernovae found with Pan-STARRS, many of them at the MMT. But of course, that's not the infrared, the rest frame infrared. For that, you need a tool that works really well in the infrared, and we used Space Telescope. So we did SN1A in the IR. It's not an acronym, it's an anagram. So we just shuffled the letters around. Here from Carnegie, you can see what the light curves look like in these infrared bands. So here's B, the blue band, where the supernova has its characteristic shape and the diffusion and so on. But the infrared bands are quite independent. They carry different information. They have a second maximum, and that's kind of a useful thing. So we have a big sample from the CFA, which we have published, and we're turning that into something comparable to this for templates. And Arturo Avellino's working on that. How do you get the infrared? Well, you find the supernova, you get the spectrum, you go to the Space Telescope, and you hope that they will move quickly, or you hope that Avishai has not got priority to use the telescope that day. Anyway, you hope that you'll be able to get the observations. The Space Telescope data, the subtractions are just beautiful because, of course, the seeing is not an issue. And Pete Chalice, Arturo Avellino, and Casey Mandel have been working on the light curves. So here are the Pan-STARRS light curves, the 4 bands from the ground that were done as part of that medium deep survey. And you can see they often sample the maximum quite well. And here are the infrared points with Space Telescope. So we can fit those, we can use that information to make a Hubble diagram. This is a very preliminary one, but I'm proud to show it because we haven't had a Hubble diagram of these things until yesterday. So anyway, we're getting there. The point is that the near infrared really helps you. So we made the case to the Space Telescope Time Allocation Committee that we were on the right track and asked for more of this, because we realized that if you did more of this and did it at higher redshift, a little bit higher redshift, about a half, you could really make a measurement where the uncertainty in the equation of state for the dark energy, if you parameterize it in this simple way, would be about 0.07, whereas the world standard at the moment is 0.06. So we could do something comparable to the world standard with a sample of about 50 objects. So we're still on the path. For cycle 23, we've been working with the Dark Energy Survey. We're external collaborators, and they find supernovae and get their light curves. Here's a nice finding chart. We get spectra, and then we put them into the Space Telescope Q. How are we doing on that? Well, you know, in California, as I said, if you have money left over, that's considered a deficit. If you have rainy weather, that's considered great. So as you may know, there has been this El Nino going on in the Pacific, and so we have not quite done as much as we had planned. We've done 9 so far. We have 60 orbits in hand for the next campaign that begins in August, so stay tuned. Thank you very much.
So my question is, what is this no-interaction model? For example,
I don't know.
How much nickel is there? How does it distribute? Does it define the way?
Oh, it's not us. We just took it right out of the...
Oh, so you say I should just look at case and what is said?
Yeah, we just look at case. So
well, it doesn't say.
It's just like it's a more or less constant. Well, it's a slightly changing temperature and radius.
All I'm saying, in Kaizen, it's not defined how much nickel there is. And there are works, for example, like Tony Pirro, show that the nickel distribution changed, the colors, roughly what you see. So.
Yeah, that's right. Yeah, so it's the early light curve, of course, is a probe of the distribution of the energy source as well and the heating of the atmosphere for the white dwarf. There's no doubt about it. And a more sophisticated understanding of that is, I think, a good thing.
Was there anything different about the spectra of that supernova?
No, that's what's so interesting about it. It's a pretty dull, ordinary supernova. So I think the conceptual part is really troubling. If it turns out this is a well-behaved, spectroscopically normal 1A, and it has a companion, let's suppose that's the story, and the other path is not excluded, that you would also have objects which were 2 white dwarfs and make something that looked like a white dwarf and so on. Then it would, it looks like a 1A. Then, you know, it's a little surprising that the class as a whole, which we haven't sorted out properly, is so homogeneous, if they really have different origins and appear so similar. So I think we're missing something. I think we need to look more maybe at the supernovae and ellipticals, or anyway, try to understand what the observational and environmental circumstances would be that would help us separate these 2 stories.
Bob, just to be mean, I would argue that you know, the observed curve is actually orthogonal to all the models, so it's clearly ruled out.
Orthogonal? Oh.
It goes through all of them.
It doesn't tell which one is right, that's for sure.
Bob, since we know that many stars are in 3-body systems, it's quite possible that you have 2 white dwarfs merging and a companion nearby, so that should be considered as a possibility as well.
Yeah, my guess is that generally speaking, the distance is quite a lot larger than the
Right.
angle.
So what is the that leads to my question? What is the constraint on the distance given these models?
I don't know the answer to that question.
I was just going to, for Avi's question, I was just going to say that Dan's models assume your Roche lobe overfilling, so the distance is always the radius of the companion, and that's going to subtend the largest angle, you know, for the ejecta. That's all.
Whereas for a third body in a 3-body, where, you know, there's no, I don't know, it might be a time scale sort of thing that says what that scale, what that radius is.
So, Robert, I just wanted to see if you could comment. 2012 CG also had this excess at late times due to the cobalt-57. But Kate McGuire looked for H alpha, and as you know, saw no H alpha. So I was wondering if you could comment on that issue.
Well, you know, it depends on the physical conditions of the hydrogen. It depends on, you simply don't know whether you should see see something, then explaining it is important. Where you don't see it, there could be many explanations. So I really don't know the answer, but it would have been nice, because then you would say, okay, there was such a star, there was plenty of gas in the neighborhood. But I think you can push the limits on the amount of gas down quite a bit. So, it's not decisive. It's hard to prove things by not seeing. It's more stimulating when you see something that you think is the signature, especially if it's close to the prediction. But the prediction is very simple, and it could be that we'll know a lot more about what the early time behavior for 1A is by